Hi, everybody. My name is Jack, and I'm coming to you from Hamilton College in the lovely upstate New York. Today, I'm going to be talking about the dice throwing problem. So the dice throwing problem is you are given n die with m faces numbered 1 to m. And you're trying to find the number of ways to get the sum x from the n die. And x is the summation of values on each face when all the dice are thrown. So if you're new to programming or even already a pretty good programmer, this problem is really tricky to just jump in and code. The true beauty is understanding the process and reasoning of what's happening in the problem and how that can be implemented in code. And I think to really get a foundation of understanding of what's going on, it's really helpful if we go over a simpler problem first. So if you have any background with computer science or math, there's a pretty good chance that you recognize this sequence. Anyways, what we're trying to do is find a function fib of n that returns the nth Fibonacci number. If you don't know how the Fibonacci sequence works, if you choose any number at random, say the 13, you can look at the previous two numbers, the 5 and the 8. 13 is the sum of those two numbers. So essentially, you have the nth Fibonacci number is equal to the Fibonacci number before that plus the Fibonacci 2 before that. Pretty intuitive so far, but what happens, say, when we're looking for fib of 1, and then it says fib of 1 is equal to fib of 0 plus fib of -1? That can't work. So this is an important step in all dynamic programming problems, is you need to establish some base cases. Luckily, in this case, they're pretty simple, and you just have when n equals 1, you return 1, and when n equals 2, you return 1. Let's jump in and code this. All right, so when I'm coding today, I'm going to be using Python 3 to be specific. If you're following along in a different language or you just don't know Python, I don't think I'm doing anything too crazy today, so you should be able to do something similar in whatever language. Anyways, so to code our fib function, we know we have to establish the base cases, and those are if n is 1 or 2, and in that case, we just return 1. And outside of that, we just return the Fibonacci number of the value 1 before, plus the Fibonacci number of the value 2 before. And down in our main function, I have 4 examples, and they should return 8, 13, 34 in this number respectively. Let's see what happens. Syntax error, I forgot the plus sign, not ready to go, 8, 13, 34, but you can see that the last call is taking a really long time. In fact, we still haven't got it. And this is where dynamic programming comes in. So let's take a closer look at what is actually happening in these calls and understand why the last call is taking such a long time. So the way that we can model an example is to make a binary tree where each node of the tree represents a function call to the Fibonacci function. So our root node is going to be our master call, which is 6. We know that then when we run through fib of 6, there are 2 calls made, the first to fib of 5 and the second to fib of 4. However, we know that the n-1 call is made first. And so when that call is made, we're now in 5, and then the n-1 call is made to 4, and then the n-1 call is made to 3, and so on all the way until we hit our first base case. When we hit a base case, we know that the 1 is returned up, and then we finally can go to a right subtree where we also hit a base case, and in this case, a 1 is returned up, and the 3 combines the 1s into a 2, and the 2 is returned to the 4. And then we would go to 4 as the right subtree, which is 2, and a 1 will be returned, and so on and so forth. Let's just keep filling this tree out until we get all base cases. And because each base case returns a 1, we know that the number of base cases we hit will end up being our fib value. And if I counted correctly, we have 8 base cases, which corresponds to the 6th Fibonacci number. So that's all looking good. However, I hope you guys just looking at the tree can kind of understand why when we tried to input 50, it took such a long time. In fact, doing a quick time complexity analysis, we know that the height of the tree is n-1, and then on each level, because each node has 2 children, the number of nodes increases by 2. So say we had 50 as the root, there would be 1 node at the top, 2 on the second level, 4, 8, 16, which is 2 to the n. And since 2 to the n dominates n-1, we have a runtime of O of 2 to the n, which is exponential, which is not good. And yeah, like I said, just looking at our binary tree, it's pretty obvious that there are some ways that we can improve it. There are a lot of duplicate subtrees. Like, do we really need to calculate fib4 twice? And so what I like to do is to create a list of values that we've already found, and then a corresponding dictionary where every value in the list is a key to the Fibonacci value. All right, let's jump back to our code. All right, so we're back with our Fibonacci function. We just need to add the empty list of the numbers calculated. So that's an empty list, and the fib values, which is a dictionary. And then for each n that isn't a base case, we just append it to the list. And then instead of returning these values, we're going to set fib values of n equal to the calls. And then we can just return fib values n. And then this is the most important step. Whenever we enter the fib calls, we can just check for if n in numbers calculated. So what this logic does is it's going to tell us whether we've already calculated that Fibonacci value or not. So then we can just return fib values of n. All right, so we have our 4 calls, and let's see what happens. We get all 4 just like that. So that's a big improvement. Let's take a look at the diagram of this function and see what changed. All right, so we're going to model our new function with fib of 6. If you don't remember, that returns 8. And as you can see on the screen, we now have a list and a dictionary where we'll be storing n's and their Fibonacci values. So we start with the root 6, we traverse down the left subtree until we hit a base case. We hit another, the right subtree of 3 is also a base case. So we have our value of 3, we put it in the list, and then we attach, we put the key and the value into the dictionary, and then we can get 4's value. So we put 4 in the list, put its Fibonacci value into the dictionary, and then as you'll see, when we do the right subtree of 5, we get 3. And because 3 is in the list, we can get its Fibonacci value from the dictionary. And so we don't need to call any more function, or we don't need to use a recursive call at all. We can just get the value from the dictionary. And so we add those values, and then we go to 6's right subtree, and it's the same case. 4 is already in the list. Therefore, we already have its value. So it's 6, 8, looking good. And then we can do a quick time complexity analysis, still have a height of n minus 1. There are 2 nodes on each level. Therefore, our time complexity is O of n, which is a huge improvement from exponential to linear. So that's a big improvement. There's a second strategy we could have used that I'll be showing us later, but I think we're ready to take a look at our dice throwing problem. All right, so now we're going to attempt to create a model for our dice throwing problem. Just as a refresher, in the dice throwing problem, we have n dice and a singular die has m sides, and we have a target value of x. And like any other dynamic programming problem, it's very important to think about, what is this problem asking, and what is an approach that makes sense? And I think it's a very smart idea to start with simpler models, and then if you want, you can work your way up to more complicated models. So I'm going to have us consider the dice throwing problem with inputs m equals 2, n equals 4, and x equals 6. I chose m equals 2 because instead of dealing with something like an 8-sided die that would overcomplicate, the problem, we now have essentially a coin flip. And so we have 4 dice to roll, and we're going for a value of 6. So how I first started thinking about this problem is, say we've already reached our goal. That is, we have 4 dice rolled and we've hit our value of 6. Looking good. Now, I want you to think about the last die that was rolled before we got to this position. Because we picked an m value of 2, there's only 2 possible values that the very last die could have been. It was either a 1 or it was a 2. There are no other values. If it was a 1, then before that die was rolled, we had a situation where we had 3 die rolled for a value of 5. Conversely, if the very last die rolled was a 2, then we would have a situation where we had 3 dice rolled for a value of 4. Okay, so how I would think about our tree so far is, because the only values that we can get from a singular dice roll are 1 and 2, the amount of combinations possible for 4 dice with a target value of 6 is equal to the sum of the possible combinations of 3 dice with targets of 5 and 4 respectively. I cannot stress the importance of understanding even just our models so far, because this pattern will continue for essentially our whole tree, and all we have left to do is determine what base cases mean what. All right, so I'm going to include a little diagram off to the right that kind of at any node nx gives us the values of their children. So we continue down another level, and you'll notice that each level you descend of the tree, the n value is always equal, and it's always 1 less than the n value in the level above. And I'd make an argument that using some smart logical thinking here, we already have a base case. And that base case is the node on the very far right of 2, 2. Why is 2, 2 a base case? Well, I'm going to argue right now that if n is equal to x, so that's the two values represented in the model, then we know that the return value is going to be 1. I think pretty logically, we can think through this together. For example, imagine that we have just 3 regular 6-sided dice. If we roll a 2 with our first roll, can we combine the other 2 dice to get a total value of 3 if we roll 2 with one of the die? No. The only possible way when n equals x to get that x value is to only roll 1s. Therefore, whenever n is equal to x, we can return a value of 1, and therefore we have our first base case. All right, so continuing down the tree, we find some more base cases. There's one right there, another one. And because 2, 2 already is a base case, we don't need to have any children out of it. So we notice at this level, all the n's are 1, and we could probably do some pretty intuitive thinking to make this level the base cases. Coming to the top of my head, we could say something like, if x is less than the greatest value of m, then it returns 1. But I think it makes more sense to go down one more layer until we have 0 die left. And I'm going to do that. So once we finish this process here, we'll notice that all of our nodes at this level have 0 die rolls left. How should we interpret the x values? Well, if the x value is 0, that means all of our rolls combine to add up for the original desired target value, which means that these nodes represent the path from the root to a correct solution. If the x value at this level is greater than 0, our values were too small, and vice versa. If the x values is less than 0, our die rolls were larger than our target value. All right, so all the base cases that will return a 1, aka the paths from the root node that generate the correct target value, are underlined in red. And I'm gonna just flash these arrays right there. So if you were to trace, remember 1 is to the left and 2 is to the right. If you trace these arrays through the diagram, you will end up at one of these correct base cases. But remember, in the dice throwing problem, we are looking for the number of combinations, not the combinations themselves. So we know for our current input, that gives us a value of 6. Also, I hope you picked up on the fact that we do have some repeat subtrees, and therefore we have some room for improvement upon our algorithm. However, like I mentioned earlier, it's always a good idea to go for correctness first and then efficiency later. And I want to take a quick look at another example. This time we have a 6-sided die. We only have 2 dice and we're aiming for 4. All right, so now, because we are dealing with a die that has 6 sides instead of 2, when we're thinking about the last die rolled, there's more than 2 values. The last die could be a 6, it could be a 5, it could be a 4, it could be a 3, it could be a 2, and it could be a 1. So this model is going to look different, and it's going to look something like this. Each node is going to have 6 children. And the reason I'm including this model here, I'll start drawing it out a little bit. You have your final 2, 4. You can roll a 1 to give you 1, 3. If you roll 2, 1, 2, 1, 1, etc., etc. But the reason I included this model is to just reinforce the idea that it's always a good idea to start working with as simple a model as possible. Even choosing an M value of 3 instead of an M value of 2 probably would have complicated my model and made it harder for me to understand how to solve this problem right off the bat. And I'm going to show you what a second level would look like. But because I did not feel like creating 36 nodes, I only did it for that node. But this third level would have 36 nodes in total. Hopefully you could figure this out. Each node has 6 children, and therefore you have a big O of 6 to the n, which really isn't great. But like I said, we're going for correctness, not efficiency. And as I was saying earlier, I just wanted to make a point that working with simple diagrams is usually better. All right, let's go code this problem up. All right, so we're back with our text editor. And as you can see in our main function, where we have 3 calls to the dice throwing function with varying inputs. First, you give me 6, second, you give me 3, and we'll worry about the third when it comes to it. But we know right off the bat that the base cases will be when n is equal to x, we return 1. And this statement right here is not only going to take care of when n is 5 and x is 5, but also on our final level, when they're both zeros, it will take care of that too. And then every other scenario where there's not a match is going to be represented on the final level when n is equal to 0 and x does not equal 0. And then in that case, you just return 0. So these 2 conditional statements take care of every single situation. And now we just need a way to iterate through every possible die value. Also, I should get rid of those. That's for later. We need a total solutions variable just to keep track of the number of successful paths. We'll set that to 0 right at the bat, and then we need to iterate across every possible die value. So we'll say for die value in range, and remember, the lowest possible die value is 1, and the highest possible is m, but Python starts counting at 0, so you need to throw in a 1. So that's going to iterate across every die value, and then we just change total solutions by dice throwing of the m value doesn't change, the n value decreases by 1, and the x value decreases by the die value. And then we just return our total solutions. So this should grant us 6, 3, which it does, but this last input, even though it's only 25, is still way too high because our time complexity is too high, and it's not going to calculate that. But like we said when we were looking at our diagram, there are subtrees, and therefore we have some room for improvement. All right, so to improve the efficiency of our code, we can do something very similar to what we did in the Fibonacci example. But quickly, I just want to talk about, I created a list, tuples calculated in a dictionary values. And I ran into a problem earlier where they weren't resetting each time I called the function. So I guess that's embedded in Python. So that means when we do our second and third calls here, we just need to send an empty list and an empty dictionary. But anyways, so we know we have to store that the values we get for our keys. And in this case, if we think back to our diagram, our keys were the tuples n, x. So what I'm going to do is I'm a tuples calculated dot append the tuples, and then I am going to set the values of that tuple to the total solutions. And then doesn't matter which one of these returns. What is important for us to do though is to check if we've already calculated something. So we'll say if nx, that's the tuple that we get, is in tuples calculated, then we just simply return values of the tuple. And so we can test our code really quickly. And we get 6, 3, and this big number, which we didn't get before we did this. So we can already tell off the bat that that is a good improvement. And we got our correctness for the first two. So we're looking good.
All right. Earlier, I teased that there was a different way to approach dynamic programming problems. So what we've been doing so far is kind of working with our final case and then breaking it down bit by bit until we reached our base cases. So that's kind of like a brute force top down with memoization. Those are the fancy terms for that strategy. And then there's a different strategy where you start with the base cases and then work your way up until you hit your intended target. As you can maybe guess from the screen right now, this strategy is called tabulation. And the name is kind of derived from the strategy. We essentially build a table from the bottom up. And this strategy, it revolves around how the base cases affect their neighbors. And in Fibonacci's case, we had the nth Fibonacci number is equal to the Fibonacci number 1 before that, plus the Fibonacci number 2 before that. And so at any given position in the table, you know that that number is part of the sum of the next two numbers. I hope that makes sense, but we can initialize the table to all zeros, but we know that the first Fibonacci number is a 1, so we put it into the table at position 1. And this is an important note about tabulation. A lot of the times, the length of your array is going to be the n plus 1. Notice that even though our last number is 7, the length of this array is 8. And that's because the 0 isn't really included within the Fibonacci numbers, but it's an important base case. So the next thing that you do is just iterate through the table. So we start at position 0, and then we add that 0 to the 1 position 1 and position 2. But because 0 is the identity in addition, those don't change. And then we just shift down 1. And then you take the 1 and you add it to position 2 and 3 to get 1 and 1. And then you shift down, and so on and so forth, 2 and 1. And you can kind of see the Fibonacci sequence. When we leave the position, you can see the Fibonacci sequence building up. And then here, and this is something that you might have seen coming, is as we get closer to the end, the positions that we want to add to end up out of bounds. And, at the end of the day, that's just some conditional logic that we'll need to include in our code. But we keep going, and then, that just disappears all the way until we get the 13 we wanted. So that worked. And for the sake of chopping off some time to this video, I'm not going to code this up. If it's a challenge that you want to take on, I challenge you to code this up. Anyways, oh yeah, the time complexity analysis. Pretty simple. We just have to do two things for each table, position within the table. So that's linear time, which is also an improvement from our original game plan. So let's try to, think about how we could apply this strategy to our dice throwing problem. All right, so this is how I set up the tabulation for our dice throwing problem. And note that I took, shit. Okay. All right, so this is how I set the table up for our dice throwing problem. And I have returned to our input where we have a two-sided die. We have 4 dice and we're aiming for 6. And as you can see, our table is of length 7, which is again our n+1. And when we're thinking about base cases, what jumps out to me is, think about 0. I don't think it's possible to roll 0 at any point ever. And I don't like, you can disagree with me, but I'm kind of confident in that. So we can put the empty array at 0. And now that we have our base case, we can start iterating through the table. But what do we do when we iterate? And this is where the work that we've already done with our previous method kind of helps us, is we know that it's kind of a story of what do you roll? Rather than working, but instead of doing the last die and then working our way to 0 die, we're working from 0 die until we've rolled 4 die. And so from our empty array, we're starting at position 0. Our only possible rolls are 1 and 2. Rolling a 1 would give us a value of 1. So we place the array 1 in position 1 and the array 2 in position 2. So now that we are done with everything at position 0, we move to the next location within the table, which is 1. And here we have the array 1. And so what 1 is it's saying we've rolled 1 die already. That's the size of the array, and its value is 1. And once again, we have a situation where not what's now our second die, but it can either be a 1 or it can be a 2. So if we roll a 1, then the array 1, 1 would go in position 2, and the array 1, 2 would go in position 3. And now there's nothing left at position 1. We can leave the table at 1 and go to 2. And I hope you're seeing the pattern here. For each position, we go through every array, and then we add each possible die value to the array and move it to the correct location within the table. So we're at 2 now. And then we have 2, 1 if we roll a 1, and 2, 2 if we roll a 2. Then we go to 1, 1 within the table. And from there, we have 1, 1, 1 and 1, 1, 2. We're done at position 2. We move down to position 3. And kind of do the same process here. 1, 2, 1, 1, 2, 2. Then we go to 2, 1. I hope intuitively that this makes sense to you. It should. It's essentially the reverse of our previous strategy. And like our previous strategy, now instead of having to think about what are the base cases, we can think about, what are the final cases. And I'll keep moving along this table at position 4. And then we hit 1, 1, 1, 1. Hopefully, you can describe what this array means. If not, I'll do it for you. So there are 4 ones within this array. What that means is you've rolled 4 die, and each time they were ones. You've rolled 4 ones consecutively. Because we only have 4 dice, you can't attach anything else to this array. Position 4 is where this array is going to stay because that's where its 4 dice put it. So we don't add a 1 and put it in position 5. We just are done with that array. And that's the case for every array within this table that has a length 4. So I'm going to put that green line under them. So that signifies arrays that we do not move. So we go to position 5, and now we go to 1, 2, 2. And as you can I hope you can kind of put this together, but sure, the array 1, 2, 2 would go in position 7, but we're only worried about position 6. Position 7 is not going to give us any information related to position 6. So we don't really need to do anything with position 7. So we'll just add the ones where necessary. And then we're done with position 5. We move to position 6. And we don't need to do anything. We have 6 arrays of length 4 at position 6, which matches with our previous answer of 6 for this array, or pardon me, for these inputs. And because once again, I haven't looked, but I'm feeling very strongly that if you compared these 6 arrays with the 6 arrays when we did the diagram for our previous strategy, that they would be exactly the same. And I haven't looked, but I am extremely confident. And once again, to save time, I'm not going to code this. Actually, I'm not going to code this live. I'm just going to walk you guys through my code. To everybody still watching, thank you. I really appreciate your support. And to my professor, I'm sorry. I didn't want the video to exceed 30-ish minutes, but it's looking like that's going to be the case. Anyways, let's just go over the implementation of the table. I set the table as a one-dimensional array. And then to get the length as the target plus 1, I used this. And then I found that they were really, first, there's something in the initialization that I didn't do in the diagram that I did in my code, and that was to set the arrays that only contained 1 value in their correct positions. And to do that, there are 2 possible cases. And the first is if your target value is bigger than your largest M value, then you can just do that for every possible die value. Whereas if it's not, which means if you roll the highest die value, you immediately exceed your table. I basically just set the arrays that only contained 1 number within them to where I could. And then here's where the code kind of loses efficiency. You have to do a double nested for loop because you need to iterate across every position. You need to do every die value, and they need to do every array at that position. And then this just checks to see if your position plus your die value is still in your table. Maybe throw an x plus 1 in there and see what happens. less than or equal to x, x plus 1, less than or equal to x plus 1. I think that's a better way to do it. Anyways, and then this checks to make sure that you haven't used up all your die rolls, and then you just copy the array, you add the die value to it, and then you put it in its new position. And then possible combinations is 0. And then for every array at your intended position, it checks to see if the length of the array is the amount. This should actually be x. I don't know why I was worried about that. So if the array had used up all the die, and you add 1, and you can see with our inputs we get the correct 6, the correct 3, but as you might have guessed, because of the double nested for loop, this value isn't going to return. Anyways, I hope you guys enjoyed this video and it taught you a little bit something about how to approach dynamic programming problems. And hopefully my ideas were captivating and kept you on the edge of your seat. And now I just want to say something to my professor, but I guess if you guys want to keep watching, you can. I just want to say thank you, Professor David Perkins. He was really great. I know the semester had tough conditions, but I found that you were understanding and I enjoyed your classes a lot. I hit a little bit of a rough patch in the middle of the semester, but I thought that you were fair, and I just want to say thanks. All right, that's it for the video. Thank you.